So I was talking about variables in C and how they're just data in memory, right? Which for pretty much any programming language is true. But one thing that really brings the power of C out is that when we know how the memory layout of C programs or on embedded systems is used and set up, it gets a lot easier to use complex data types, arrays, structures, which we'll get into later. So having a really basic, even abstract understanding of memory and how a program structures memory is quite important. So I'm not going to go into the details of like stacks and how they're used and how all of this sort of like functions are entered and whatnot. But there's basically two memory regions when you're writing a C program that are relevant to you. And they are called, we have the stack and we have the heap. Now, the stack is generally, without going into depth, it's just some sort of temporary data, and it's like like a normal stack. You push things onto it, you pop things off of it, right? But what happens in the stack when you go into a function is that variables that you use in your function are created temporarily, meaning as soon as the function returns, these variables that you created are popped and they're destroyed, right? They're no longer accessible. While they still exist somewhere in memory, if you were to access that memory directly, you could probably cause memory errors, and this is really not what you should, it's not a supported behavior, and it's definitely not recommended. And so then you have the heap, which is a memory region where you can dynamically allocate things, meaning that the user at runtime can allocate memory regions to store variables that aren't tied to like a function or a context, or like as I say, have here a scope. So a scope being when you enter a loop, there's a stack for the loop, or there's variables that are only in that scope of the loop. Same with a function. And so it's really important to know that there's these two different regions where your variables exist, and because it really defines where the variables are accessible from. So the heap and the stack both exist in a region of your program or memory, and they grow. So they grow sequentially. So when the program starts, and for instance you have nothing on the stack or nothing on your heap, the memory the memory management part of your program, of your system, your kernel, your operating system, what have you, sets the next memory block available to either a low address or a high address, as we can see here on the left. And as you create variables in your functions, pushing them onto the stack, or if you dynamically allocate memory regions on the heap, you're growing these pointers, you're growing this address. And so you're just creating your data, your variables in memory, and it happens sequentially. So when you create like an integer, it will come here, and the next one you come here. And if you create an array, it'll be a number of variables going up towards a high address, and then the stack can go down. And so you can imagine you do have a fixed amount of memory because these two regions can collide, and then you get into really bad memory issues. If you're running on a laptop, usually these sort of things aren't a big problem, but when you come into an embedded system where you're really on a memory constrained device, this can become a big problem. So now we'll quickly go and talk about the stack a bit more. So a good example would be, this is something that's really demonstrated best in example. So I'll give a code example for this in a minute. But really, this is where local variables live. So when you create a function and you say, you enter your function and you say int foo equals 1, right? You've created an integer variable within a function, and so you can say in this regard that this variable exists in the scope of this function, and therefore it comes onto the stack. So I'll mention in the next slide when we talk about the heap, anything that's really created using just like int, like some data type, some name, something, is created on the stack. There's a few moments where this might not be true, but in general, when you're entering some sort of a function or a loop, then you're creating these sort of local variables, and their lifetime is bound to where they were created. So as soon as the function returns, these variables that you created within your function, they cease to exist, right? And because as you enter a function, you enter a function, you enter a function, you're having these scopes, and they're sort of stacked on top of each other, when you create sort of stacks and stacks and stacks that then pop off when the functions return, and so these variables get destroyed. So then we'll look at the heap now. So this should say heap. So the memory on the heap is allocated and deallocated by the program's design. So this means that the user really does this manually by calling a set of alloc functions. So this is malloc, realloc, calloc, and then they can free the memory regions by using free. Now, so the big difference is that let's say you want to enter a function and then enter another function, but you always want to have one variable or some sort of data in memory not getting destroyed as these contexts pop off of their stacks get destroyed. So what you would do is you'd say, hey, I want to allocate this chunk of memory here to store this integer, and I don't want it to get bound to the context or the scope of this function. And so this is what we call dynamic memory allocation, and this is when you're allocating a chunk or a region of memory on the heap. And so it's up to the user or the programmer then to allocate the memory region, to check that it was allocated correctly, which you can then use, it's a valid piece of memory, but then when you're finished with it, you should make sure that you free it. And so you sort of saying, okay, I don't need this block of memory anymore, because if you don't free it, you can imagine if, let's say, you're having loops that constantly create or allocate memory regions, at some point you will have used up all of your memory. And so you need to be smart about making sure that you sort of use the memory when you need it, but keep aware of the lifetime of the actual memory and when it's needed, and then to get rid of it when you don't need it, right? So let's look at sort of a bit of an example, if you will. So here on the left we have just a random, like this could be a stack or a heap. So it's just some continuous block of memory with some address, and then we have the content. So each byte, as you can see here, because it's 2 hexadecimal characters, so this is a byte, and this is the address of this byte. And so when we create them, we actually the addresses just increment and our data gets put into it, right? So as you can see here, if this was some sort of this example on the right here was in a function, firstly sum was created because you said, hey, I want an integer called sum with a value of 255. And so that will just get put here onto into memory. And the endianness of the system, so this is whether the most significant byte comes at the beginning or at the end of memory, determines the order. But as we can see here, the value is 255, and so in memory we have essentially this is the least significant byte stored in the most significant in the largest memory address. So off the top of my head, I think this is big Indian. I can't remember. This is not something that we'll really talk about. This is stuff that's handled automatically by the compiler, because we don't really care in the order of the bytes. All we care about is the order of these variables in memory and their sizes, because when we dereference an integer in memory, the compiler who compiles our program actually handles the managing of the endianness of our data. So yeah, going on with this, we created an integer sum, which we can see in memory here. This is this 0000000FF, and then we've created an age -1, and so this is a short, and so -1 is represented by 4 Fs in hex, and we can see this in memory here. And so if we were to keep going on, this next one would be a double, so this is an 8 bytes, and this would be its value, and so you can see that this ends up in memory and so forth, right? So I will go do an example now for memory layout.